There is a problem in mathematics that has gone unsolved for nearly a century. The funny thing about this problem is it's quite easy to understand, even for a middle schooler. The problem involves two separate rules. If the number is odd, you multiply it by 3 and add 1. If it's even, you divide it by 2, essentially getting rid of 2 as a prime factor. The question is, under iteration, does every single number eventually reduce to 1? Today, I plan to take you on a unique journey through the Collatz Conjecture. We begin our journey with the function in its standard form. If the number is odd, we multiply it by 3 and add 1. If the number is even, we divide it by 2 until it becomes odd. Because we keep dividing it by 2 until it becomes odd, we can use a shortcut where, if it's even, we divide x by the largest power of 2 that divides x. To begin, we select a seed. For this demonstration, I'll use 9. Since 9 is odd, we multiply it by 3 and add 1, which brings us to 28. Visualizing 28 as its prime factorization, we see that it's equal to 2 to the power of 2 multiplied by 7. Since we can see that the largest prime power of 2 that divides 28 is 2, we know that there would be 2 halving steps to divide 28 down to 7. Now, traditionally, we would multiply 7 by 3 and add 1 because it's odd. But instead, we're going to define a new function that combines both the rules. The new function is 3x plus 2 to the n, where 2 to the n is the largest power of 2 that divides x. And what we're going to want to do is factor the 2 to the power of 2 back into the number 7. Now, traditionally, when we reduce the number to its odd form, we would add 1 to send it to its consecutive coprime state, or its next successor. But what we've essentially done is made 4 separate copies of that odd number. So instead of adding 1, we have to add that number 4, or the largest power of 2 that divided 28. Now, if we go back to the traditional function, multiplying 7 by 3 and then adding 1 would originally give us 22, which has a prime factorization of 2 to the power of 1 times 11 to the power of 1. This provides us with one more halving step. Combined with the 2 previous halving steps, this is a total of 3 halving steps, which would bring us to 11. Miraculously, referring to the single rule iterative function where we multiplied x by 3 and added the largest power of 2 that divided x, in this case 28, this brings us to 88, which has a prime factorization of 2 to the 3 times 11 to the 1. What's imperative to notice is by skipping the halving steps, we've essentially carried them along with us, recording them in the exponent of the largest power of 2 that divides x. What this means is, we've traded 1 for the largest power of 2 that divides x as the next successor, or the unit. This translates to a successor function that marches along the power of 2 axes, or, more formally speaking, the 2-adic ring. What this does is, because it's a successor function marching along the 2-adic ring, it makes it structurally inevitable for the function to intersect a prime power of 2. We can visualize this by taking all of the halving steps and compressing them to a single trajectory, while also isolating the total value of x during each iteration for full resolution. Also, since having prime powers of 2 has a deterministic trajectory that ends at the number 1, this provides a structural evaluation of the Collatz conjecture in which all numbers eventually reduce to 1. or, more straightforward, proving the Collatz conjecture true.